In this module, we shall introduce the concept of estimability of functionals. We shall introduce the concept of kernels and some associated issues. We shall define symmetry and asymmetry of kernels and supported by a number of examples. Lastly, we shall explain the concept of statistic as parallel to unbiased estimation in parametric inference. All these are supported by a number of examples. In parametric inference, we have estimation where the objective is to put some value close to the actual parameter. In parametric inference, we also have hypothesis testing where the idea is to verify the validity of assumption regarding the unknown parameter by means of data. Lastly, we have confidence interval estimation where we try to develop a random interval which contains the unknown parameter with high probability. A non-parametric inference procedure has also the same three components, but these problems are tackled in a different way as the underlying distribution is not at least known functionally. We start with non-parametric estimation. Before we go into the details, we refresh some concepts in the context of non-parametric inference. So, we start with estimability. What is estimability? In the language of parametric inference, if we can find at least one unbiased estimator for a parametric function, then it is estimable. In non-parametric inference, the idea is same but with different terminology. We have already introduced functional and statistical functional or plug-in estimators. Suppose x1, x2, xn are IID observations from f and theta f is a functional defined on script f, the class of all absolutely continuous distribution functions. Then theta f is said to be estimable if there exists a function phi, where phi is a function of k elements, that is a function of x1, x2, xk, where k is strictly less than n. Then if expected value of phi under f is theta f for every choice of distributions from the class of distributions, then theta is said to be estimable. Now, phi is known as a kernel of degree k because this phi involves k observations. This k is known as the degree of phi and phi is called a kernel. Minimum value of k ensuring the above, that is expectation of phi equal to theta f, is called the degree of the kernel. Therefore, kernels are in some sense the analog of an unbiased estimator, except that it is not based on the full set of observations and to each kernel a degree is attached. In parametric inference, the sum of two unbiased estimators is also unbiased for the sum of parametric functions. So, what can we say in non-parametric case? Suppose phi1 is a kernel of degree k1 for the functional theta1 and phi2 is a kernel of degree k2 for theta2. So, what will be the degree of phi1 plus phi2? Observe that phi1 plus phi2 is a kernel for theta1 plus theta2, but keep it in mind that few observations can be common between phi1 and phi2. So, we start with assuming k1 less than k2. Then phi1 plus phi2 is based on at most k2 observations. On the other hand, if k1 greater than k2, then phi1 plus phi2 is based on at most k1 observations. So, in any case, phi1 plus phi2 involves at most maximum of K1 and K2 observations. Therefore, degree of phi1 plus phi2 is at most maximum of K1 and K2, and the same can be said if we use the difference kernel. That is, if we use phi1 minus phi2, then phi1 minus phi2 will be a kernel of degree at most K1, K2 for theta1 minus theta2. So we can easily generalize to a number of kernels. Suppose we have S kernels phi1, phi2, phi s with degrees K1, K2, Ks. Then degree of the summation I from 1 to S phi I, that is the sum of the kernels, cannot exceed the maximum value of K1, K2, Ks, that is the maximum of the individual degrees. Now consider the product of kernels. In parametric inference, the product of two unbiased estimators is not unbiased for the product of parametric functions unless the estimators are independent. The same can also be seen in non-parametric inference. So we consider kernels phi1 and phi2 of degree K1 and K2. The corresponding functionals are theta1 and theta2. If there are some common observations in phi1 and phi2, then phi1 and phi2 are in general dependent. Therefore, their product cannot be a kernel for theta1 into theta2. Therefore, if theta1 into theta2, that is the product is the functional of interest, then phi1 phi2 is a kernel for theta1 theta2 if they are based on different sets of observations. Assume that the sets of observations corresponding to K1 and K2 are different. Then phi1 phi2 involves K1 plus K2 distinct observations. Thus, degree of phi1 phi2 is K1 plus K2, and we can easily generalize this result. So, if we have S kernels each with degree K1, K2, Ks, then the product phi I from 1 to S is a kernel for the product functional I from 1 to S theta I with degree summation I from 1 to S Ki. Thus, if we have S kernels with degrees K1, K2, Ks, then product of the kernels will be a kernel for the product functional with degree summation Ki, provided kernels are based on different sets of observations. Now, we introduce the concept of a symmetric kernel. Phi with arguments x1, x2, xk is called symmetric if phi x1, x2, xk is the same as phi xi1, xi2, xik, where i1, i2, ik is a permutation of 1, 2 up to k. Therefore, if phi is invariant to any permutation of its arguments, then phi is known as symmetric. For example, if phi is the sum of observations, that is, if phi is summation I from 1 to n xi, then the value of phi is not changed if we consider a different permutation of the observation. Thus, phi is symmetric. Easily, any function of a symmetric kernel is also a symmetric kernel. As another example, we can think of quantiles. Quantiles are also independent of the order of the data, therefore are symmetric. Then, what is an asymmetric kernel? Quite naturally, if a kernel phi is sensitive to permutation of the argument, it is asymmetric. For example, consider x1 square minus x1 x2. This x1 square minus x1 x2 is asymmetric because if we interchange x1 and x2, we get x2 square minus x1 x2, which is not the same as x1 square minus x1 x2. Thus, x1 square minus x1 x2 is not permutation invariant and therefore asymmetric. Similarly, x1 minus x2 and x1 divided by x2 are also asymmetric kernels. Now, consider another useful example. Consider phi x1, x2, x3 as x1 square plus x2 square plus x3 square minus x1, x3. It is interesting to observe that phi x1, x2, x3 and phi x3, x2, x1 are same. But phi x1, x2, x3 is not the same as phi x3, x1, x2. Therefore, phi is not invariant to any permutation. Therefore, phi is asymmetric kernel. Now, we give an interesting result, which is for every regular functional, there exists a symmetric kernel. The proof goes like this. Consider a kernel of degree k and take all the k factorial permutations of its arguments. For each set of permutation, evaluate the kernels. Then the average of these values will also be a kernel with symmetry. Therefore, without any loss of generality, kernels can be taken as symmetric. Now, we shall consider the concept of a U-statistic. Kernels are unbiased estimators, but are not based on all observations. U-statistic is the non-parametric analog of an unbiased estimator based on all observations. Consider n IID observations and a kernel of degree k. Assume that phi is symmetric. Then we can have n choose k distinct sets of k observations. For each set of observations, we can calculate the value of the kernel phi. A U-statistic is the average of all such values. Therefore, U-statistics are often called generalized means. Clearly, U-statistics are permutation invariant and based on all observations. So, for any kernel phi of degree k, U-statistic is defined as n minus k factorial divided by k factorial into the summation of phi xi1, xi2, xik, where i1, i2, ik is a permutation of the real numbers 1 up to n. If phi is symmetric, then un takes the form 1 by n choose k summation over phi xi1, xi2, xik. Let us illustrate the concept with some examples. Suppose the functional of interest is expectation of x. Since the functional is an expectation of a random variable, we take the kernel as phi x1 equal to x1. Then phi is by definition symmetric and of degree 1. The corresponding U-statistic is naturally x bar, the sample mean, actually the usual unbiased estimator. Consider the next example. Suppose script f is a class of all absolutely continuous distribution functions and theta f the probability x1 less than equal to small a, where a is known. Observe that theta f can be looked upon as expected value of indicator x1 less than equal to a. Therefore, by the analogy with the previous example, we can set the kernel as phi x1 equal to indicator x1 less than equal to a. Then phi is symmetric and of degree 1. Therefore, the corresponding U-statistic is the proportion of observations less than equal to small a, which is nothing but the usual unbiased estimator. Now, consider the estimation of mean square, that is, the square of the expected value. Since observations are IID, we can express the square of mean as expected value of x1 into x2. Thus, we take the kernel as phi x1 x2 equal to the product x1 x2. Naturally, phi x1 x2 is symmetric but of degree 2. Now, the corresponding U statistic takes the form x bar square minus s square by n. This actually can be found after little bit computation, where s square is the usual sample variance with divisor n-1. So far, we have got symmetric kernels, but kernels can be asymmetric depending on the situation. Now, consider the following examples. Suppose script f is a class of distributions with finite second order moment, and the functional of interest is the variance of x1. Now, observe that variance of x1 can be expressed as expected value of x1 square minus the square of the expected value of x1. Therefore, theta f is the difference of two quantities. Now, for the first quantity, a kernel is x1 square and a kernel for the second quantity is x1, x2. Then it is natural to consider the difference, that is x1 square minus x1, x2 as a kernel. But such a kernel is not symmetric, as we have seen in our already examples. Therefore, we symmetrize it by taking the average. Now, x1, x2 has two possible orderings, that is x1, x2 and x2, x1. For each ordering, we calculate phi and their average will be a symmetric kernel. The average comes out as half x1 minus x2 whole square, and after a tremendous simplification, the U statistic reduces to s square, the usual unbiased estimator of variance. Next, consider the estimation of expected value of x1 square. Now, expected value of x1 square is the sum of variance of x1 and the square of expected value of x1. For variance of x1, a kernel is x1 square minus x1, x2, which is of degree 2, whereas for the second, a kernel is x1, x2, which again has degree 2. Therefore, the sum, that is x1 square, is the required kernel. Then U statistic is the sample second order raw moment. But here I have some comments to share. We observe that we have two kernels of degree 2, but their sum is of degree 1. Thus, the degree of the sum of two kernels can be strictly less than 2. Again, one of the kernels is symmetric and the other asymmetric, but the resultant is symmetric. In particular, the sum of two symmetric kernels is always symmetric. For the next example, assume that observations come in pairs from some bivariate distribution. The objective is to find U statistics for the estimation of expected value of xy. The idea is very simple. Define a new variable z as xy. Then the distribution of z will have first moment finite and the distribution will be continuous. With the introduction of new variable z, the problem therefore reduces to the estimation of expected value of z. From the already discussed examples, the U statistic is z bar, that is the average of xy values. Similarly, if we consider estimation of variance of x plus y, we take the new variable z as sum of x and y, then the distribution of z is continuous with finite variance. Thus, with the redefined variable, the objective is to estimate variance of z. The corresponding U statistic is naturally s square z, that is the sample variance based on z observations. Thus, in any case, the basic idea is to define a new variable z having some univariate distribution and reduce the functional in terms of the moments of z and then apply usual methods with Z observations. We have seen how estimability of functionals are defined. We have introduced the concept of kernels and their symmetry. We have also discussed U statistics and shown that U statistics is unbiased and is symmetric in observations. However, we did not provide any property of U statistics. In the forthcoming module, we shall explain some small sample properties of U statistics.